Hello everyone, welcome to another session on machine learning series. So today we'll continue with our discussion on decision trees. Right? So previously what we basically discussed was we were discussing one of the measures of decision trees, namely information gain. Right? So we looked at how do you basically calculate information gain. Right? We looked at our data set. We basically had outlook, temperature, humidity, windy. Right? On those four columns, we basically calculated information gain on outlook column only. We basically saw how do you actually calculate information gain, and we went about discussing how does tree splitting happens, right? So just to give a sort of a recap on that, so this was basically the column, right? So we basically used column outlook, right? So column outlook basically had three unique values: sunny, overcast, and rainy. Right. So basically this was the column. This was the column on which we calculated information gain, right? Similarly, we'll do that for the other metric as well. The other metric is basically called as Gini Index. So what basically Gini Index is? Gini Index is nothing but it's a statistical measure of dispersion. Okay, statistical measure of distribution, as a matter of fact. So it's nothing but 1 minus sigma of t is equal to 0 to 1 probability of t square. What is a t? What does t denote over here? Is number of unique values. It's not a number. It's basically so you have two unique values, yes and no, right? So this is how you calculate. This is the overall Gini Index. But basically what we'll do, we'll actually calculate on a single column, right? Namely outlook, we'll calculate what would be the Gini Index, right? Let us go into that. Okay. You know what is outlook, right? You know the outlook column distribution, right? So this is outlook column. So you basically have three unique values: sunny, overcast, and rainy, correct? In sunny you have three yes, you have basically yes and a no. In overcast you have all of yes, and rainy you have three yeses and no, right? So basically what is happening over here is you basically on this column will basically calculate a Gini Index. So we'll start off with just the plain probabilities. In the first column, what you basically have, you just have your plain probabilities, right? You're saying probability of if outlook is equal to sunny, this is this value. Probability of outlook is equal to overcast is this value. Probability of rainy is this value. So that's the first step. So the next steps are you basically calculate when outlook is equal to sunny, right? When outlook is equal to sunny and play is equal to yes, what is the probability? When outlook is equal to sunny and play is equal to no, what is the probability, right? So you basically first calculate at the overall level. You calculate at sunny, overcast, and rainy. Then you basically say for in sunny, if the response value is yes, what is the probability? In sunny, if the response value is no, what is the probability? In a similar manner, in overcast, if the response value is yes, what is the probability? In overcast, if the response value is no, what is the probability? Similarly for rainy as well. So that is what this is. You calculate your probabilities over here, right? Then for each individual, you just take a plain Gini Index. So this is where you get this from. Is you get this from the formula, right? From this formula, right? You basically had 1 minus p of t square. Summation of t is equal to 0 to 1 p of t square, right? So that is this, correct? So you're just calculating for each. For sunny, you're calculating your Gini Index. For overcast, you're calculating your Gini Index, and similarly for rainy, you're calculating your Gini Index, right? But what we want basically is not just the value. We want a sort of weighted sum, right? What do you weight it with, right? Obviously you can't give some random weights. So what you weight is you weight it with your initial probabilities, overall probabilities you calculated, right? That was so say for overcast, right? For outlook is equal to sunny, this is a value 0.48. So this you multiply with 5 by 14, right? That is what happens over there, right? 0.5 by 14 to 0.48. Right? Similarly, in similar manner you will calculate for other values as well. So 0.343 is the value of your Gini Index for outlook. So in a very similar manner, you calculate for columns like windy, you calculate column for temperature, humidity, and basically the root node will be the one with the highest Gini Index, right? So this after that the process would remain the same, right? You for the next, again you get your branches, then you get your node, then again you split it, right? Again you split it, again the splitting process continues, right? So this is what is Gini Index. Finally, so when you're comparing between your Gini Index and when you compare that with information gain, right? The one which is more easier to calculate is obviously a Gini Index, because you do not have any log value over there, and that is why you see, and it is also more robust. That is why you see the Cartesian regression trees being more popular than your ID3 type of trees. Right? Because in your Cartesian regression trees, you basically use your Gini Index. So this is basically the approach which is used in your Cartesian regression trees, right? You basically calculate Gini index for each of your columns, and from there on choose the column with the highest value to be the split. And obviously the split happens. So there are certain stoppage criteria, right? So this being an iterative process, right? This whole tree building process is an iterative process. So I think whatever examples you've seen until now was on a very small data set, but obviously real world data sets would be very huge, right? It will be around, say, order of few hundreds of thousands. Then what will happen is obviously you'll have more and more levels. So you can't at that time you can't maybe go in a process where you stop only when you reach the root node or all values in that particular node are equal, right? Obviously it'll take a lot of time and effort. So instead of that, there are certain stoppage criteria, stoppage conditions. So one stoppage condition could be the max depth. So depth is basically the number of levels in your tree, right? At one level, so root node is basically the starting level. That's like level 0. After that, you're level 1, level 2, right? Maybe you can put a condition, stoppage condition saying after 8 levels it stops. That is one. Other ones could be minimum samples per leaf. So in your node, right? If it is only 10 samples, or if the sample is lesser than 10, then you basically stop your tree building process, right? These are few stoppage conditions. Obviously, as we look at more algorithms like random forest or boosting, there are certain hyperparameters over there. I think you would get a better idea of the stoppage conditions. Okay. So coming to advantages and disadvantages of decision trees, right? So one advantage, obviously, it's very easy to interpret, right? Say suppose you are trying to explain your model performance, or you're just trying to understand what features are important and things like that. So running a decision tree is one of the easiest way to understand, right? And even if you're trying to maybe explain to sort of a business people, right? You may be trying to explain to some business person a machine learning model. Obviously, in comparison to other algorithms, right? Decision tree is very easy to interpret. You can just put a decision tree on the slide. People would immediately understand what is happening, right? Coming to disadvantages, one, even though its accuracy is good, obviously it's not best performing model, but it suffers from high variance, particularly in cases where a decision tree is completely grown, right? I think you can look at the same minimum samples per leaf parameter which we were talking about, right? So assume you have around 100,000 rows, right? And if you put a minimum samples per leaf around 10, what would happen is obviously you'll get a lot of branches, you get a lot of nodes, but what will happen is your tree fits to your data, right? Overfitting happens. So that concept in bias and variance trade-off, which we discussed, overfitting and underfitting, right? This is what happens. So in decision tree, one major problem is variance. Its variance is very high, right? So obviously, if you use certain stoppage conditions and make sure a tree does not grow deep, in such cases your variance might be not very high. But say if you actually allow the tree to grow completely, or you put a very very low stoppage condition, you keep on running it for a good amount of time, then obviously decision trees are very variance. So in the next approaches which we'll discuss, namely random forest and boosting methods, over there main aim is obviously combining multiple trees, but the main aim over there was how to reduce the variance at the same time making sure your model is performing well. Okay guys, then I think in the next few sessions we'll discuss about random forest, how random forest works, how boosting works. All of them come under a class of algorithms called as ensembling. The basic idea of ensembling is you're just combining multiple trees. You can combine other sort of learners as well, but in our specific in whatever we discuss, we'll be just focusing only on trees. Okay guys, then thank you.